All right, so like I said, we left off yesterday looking at the three-dimensional parametric equations, and like the other stuff we've done in 3D, it's just another equation, a z component. So notice here, what we have is we would be given some point on the line, x0, y0, z0. And the reason why we put 0 here is because this is when the time equals 0. Okay? When you set up your equation like this, whatever point you use is going to be the point you're at when the time is 0. Also, we have here a velocity vector of ABC. Okay? So a velocity vector of ABC. Those are the parametric equations for this situation. A given point and a velocity. Okay? You could kind of think of this as point slope form. Okay? Now, when we are talking about the equation of a line in a vector form, okay, one thing that we're doing with, at least what we're going to do, is we're going to always assume that the velocity stays constant. In other words, we're going to deal with linear situations. Okay? Now, we've done a couple problems where we've hit a projectile through the air or something like that. That's not a linear situation because your velocity was changing the whole time. Okay? If we did anything like that, I'd give you those formulas, all right? But the ones that I'm going to expect you to be able to write the equations for are going to be linear in nature, constant velocity. So, we have this equation here. R is our result, or the line that we're going to have, and that is given by the position vector at time 0. In other words, that point we can write as a position vector, x sub 0, y sub 0, z sub 0. Okay? B is our velocity vector, and then t is just the scalar for time. Okay? So we could write it as an equation, r equals a plus tb. So, using the same vector and point that we have up here, notice at the bottom, we can write our vector equation where our position vector x, y, z at any given time is found by taking our position vector when we start, x sub 0, y sub 0, z sub 0, plus t times the velocity. Okay? So there's two things here. There is the vector equation. Okay? We have the vector equation. And we have parametric equations. And you should be able to convert from one to the other. All right? We'll do some of that. We'll convert from one form to the other. Some are more useful in one. Sometimes it's more useful to have it in the one. Sometimes it's more useful to have the parametric equations.
And what do these find?
Well, the kinds of things that we've been graphing have been examples of this. Okay? We've been doing it so far like in 2D. Now we can see it can be done in 3 dimensions as well. And from here on out, we'll be doing some in 2D, some in 3D as we go.
Okay, and then which equation does the parametric equation correlate to?
Well, it's always a set of parametric equations, plural. So all 3 of these go together as a set. Okay? If we had the vector equation, notice we have x, y, and z. So when you're taking this, and you'd have x equals x sub naught plus t times a. That's where we're getting this right here. X is x sub naught plus t times a. And then we could do the same thing with our y. okay, y equals y sub naught plus t times b.
So the component vector form is made up of all three parametric equations?
Yeah. So, let's start with 1 and 2 dimensions, just to kind of see this and break it down a little bit. And we'll also see what we can do with some of these. Alright? First of all, if we have the vector equation xy equals negative 2, 5 plus t times 2, negative 1, where is our starting point?
-2.
Yes. Yeah, the point is negative 2, 5. Okay? So I could graph this down here, negative 2, 1, 2, 3, 4, 5. And that is when t equals 0. Okay, there's our starting point. Okay? What is the velocity? It's the vector 2, negative 1. Okay? The vector 2, negative 1. So every second, think of it this way, every unit of time, we're going to go to the right 2 and down 1. Okay? So if we go to the right 2 and down 1, after 1 second, we're here. If we go to the right 2 more and down 1, there's another unit of time, we're there.
Oh, they're just linear equations.
It is a linear relationship because our velocity is staying constant. Okay?
It's like mx+b.
It is.
Okay.
It is kind of like mx plus b. The velocity vector is like your slope, t is like the x, and the plus b, that's your starting point. It's not a y-intercept here, but it's a starting point. Okay?
Why isn't it a y-intercept?
Well, it's at negative 2, 5. It's a time intercept. It's when the time is 0, not when x is 0. Okay? What would be our x parametric equation? Someone share with us, what would the x parametric equation be for this situation?
Coming forward, x equals -2 plus 2t.
Yeah, just the equation for x. X would be negative 2 plus 2t. Okay? And someone else give me the y parametric equation. So you are quiet, and I don't know if you're with me or not with me or lost or whatever. Help us out here. Somebody else, other than the 3 people who have answered every question so far. All right, Matthew?
Y is equal to 5 minus t.
All right, y equals 5 minus t. We've got that negative 1 in there for our velocity, so y is 5 minus t. Okay? Now, we don't necessarily need the parametric equations when we're finding these different times here, okay? Where is it when t equals 0, 1, 5, or negative 2? You're just plugging in different points. So when t is 0, 1, 5, negative 2, what is our position, x, y? Well, we're just plugging in a different value of t every time. We already know the starting point is when t is 0. And we already found when t is 1, that's the point 0, 4. Okay? We found that just by sketching. But notice here, if we want to plug in 5, you could plug it into the vector equation, or you could plug it into the parametric equations. But x is going to be negative 2 plus 10, which would be 8. And y is going to be 5 minus 5. So that's 0. So we have 1, 2, 3, 4, 5, 6, 7, 8. The point 8, 0 is when t equals 5. Okay, so 8, 0 is when t equals 5. Okay, Also, we can kind of go back in time. If we just happen to start our clock when this was at negative 2.5, we can look at where was it 2 seconds before we happen to notice it. Okay, so you plug in a negative 2, and you get negative 2 minus 4 is negative 6. And negative 2, 5 minus a negative 2 would be a positive 7. Okay, so 1, 2, 3, 4. Okay, so there's t equals a negative 2. Okay, so you can see here, there's our line. Okay, now that's all fine and good, all right. We can find some points, that's nice, all right. Where this gets more useful is when we want one of the variables, one of the x or y variables to equal something specific. Okay, we did this a little bit when we were determining whether or not a hit was a home run. We said, how far does x have to go? It's 400 feet away, or it's 314 feet away, or whatever it was in the problem. We figured out that time, and then we were able to figure out the other coordinate. Okay, so let's say that we want x to equal 10. This is where the parametric equations are useful. Okay, if x is 10, then I know that 10 has to equal a negative 2 plus 2t, and that tells me that t has to equal 6. Okay? So I solve that equation for t, and I figure out when x is 10, and now I can go back and I can figure out what value of y has an x equal to 10. Okay? So, now I know that y is 5 minus t, so that in this case is 5 minus 6, which is negative 1. So, and if you look at our picture, that makes sense. We have the point 10, negative 1, when t equals 6. Okay? And we could do it for something that's not even as close. We could say, okay, well, when is x going to equal 100? We could find the time by solving the parametric equation, then plugging it into the y, and figuring out what y would be then. Okay? So that's where these can be pretty useful. Okay? Now, here's another case where the parametric equations are useful. Look at our vector equation in 3 dimensions. Okay? The question here is, does an object pass through this point? Okay? So we have 2 points, 2, 3, 15, and negative 8, 8, negative 1. Okay? What would have to be true for the line to actually, well, the object traveling along this line to actually pass through this point?
Oh, you wouldn't pass on top?
This point to be on this line.
Oh, okay, same stuff. There would be,
No. Well, is the top one always a line? No, it's always a vector.
This one for us is always going to be a line because we don't have any variables in here. Okay?
I think there should be a certain value of t for which when you plug this value of t in the equation, you got exactly 2, 3, 15.
Okay. So there's got to be some value of t that when you plug it into the equation, you get 2, 3, 15. Okay? That's a good explanation there. Now, how do we find that value of t?
Oh, we'll split it into
Equal to
parameters.
350.
Like a table?
Equal to 350.
Just some random, just a table, you know. What if t is like 5,000 or something? You have to scroll for a while. Okay, let's find a better, a more efficient way of doing it. Okay. Or what if it's like 1.187, you know,
What's the next step?
so you're gonna be in trouble.
You
What?
have to split it up
You do.
into parametric equations and then solve for each number.
Okay, so if we have what would the parametric equations be? X equals
Minus 2
Negative two.
Oh, it does
plus
work.
2t.
negative 2 plus 2t.
And the x is 2.
Y equals,
5 plus, or 5 minus t.
yeah, 5 plus a negative t, 5 minus t.
Values of t.
And z equals
4.
7.
7
Plus 4.
plus 4t, okay?
Oh, you said 14.
Yeah, Matthew?
You skip the difference and divide by the velocity. So like, is there instead of 4 between -2 and 2, so you divide by 2 to get your time.
Yeah, and really what you're doing when you're thinking of that, you are solving these equations in your head, okay? Because you're saying, okay, in order to, it's gotta equal 2 for our x, so 2 equals negative 2 plus 2t. I add 2, so 4 equals 2t. So t has to equal 2. So my x is going to equal 2 when t equals 2. Alright? We started with our x's. And this is 2. We wanted x to be 2, right? So x is only going to equal 2 when t equals 2. Alright? So then we can do the same thing with our y's. Except the y we want to equal 3. Okay? So for our y, 3 has to equal 5 minus t. Alright? Well, I add t and subtract 3, and I get t equal to 2. So far, so good. Okay? Now I've got to try z. Okay? So, for my z's, 15 has to equal 7 plus 4t. So I subtract 7, I get 8 equals 4t, and t equals 2. So, is this point on the line?
Yeah.
Yes, because my x, y, and z will equal those values at the same time. Okay?
So if it all equals the same.
They've gotta all equal the same thing. It's not good enough just to have x and y the same and z different. You gotta have all three. Rachel?
So, like, depending on x, like, they have to be all the same, like, x kind of, like, since you do x first.
Yeah, you can do any one you want first, you know. So like here, if x is a negative 8 equals negative 2 plus 2t, you add, you get negative 6 equals 2t, so t is negative 3. So if I do y and I get something other than negative 3, I can stop, because I know my answer already. I know that point's not on the line. Okay? So if I try the y, and 8 equals 5 minus t, that means t equals a negative 3. Okay, so it's working so far. Then when I find the z, okay, does negative 1 equal 7 plus 4t when t is negative 3?
No.
Well, that's a negative 8 equals 4t, so t equals a negative 2. So that right there is different than the other two, so no. Okay? That one is the same, is different. These three were all the same, so yes. Okay? Questions? Does that make sense?
Mr. Hickson,
Mhm.
do you know any Desmos 3D?
I don't know if Desmos does 3D.
Like any type of Desmos program that shows 3D graph?
If you have Microsoft, if you have a Windows computer, there's actually a program called Microsoft Mathematics.
Mm.
It's pretty cool. It'll graph stuff in 3D. The TI Nspire will do stuff in 3D.
Oh, his calculator.
Yeah, the Nspire as well. The TI-84s won't. Okay? Alright, so that's really it for new stuff today. I want you to get used to working with these and used to seeing the vector equations and the parametric equations. So I've given you a few of these. These are not all part of the required IP, but there's extra practice if you want here. Look in your required IP document for the ones that are required, obviously. Okay, but notice on each of these, you're given a velocity. If we want a line parallel to 213, that's telling us the velocity that we want, and it passes through that point. You can use that point as your starting point. Okay? So give these a try. You've got vector equations, parametric equations that you need to get for these, and then some other problems where you actually use them. Okay? All right.